Hi guys, welcome back to our YouTube channel. Today I'm going to discuss about the ordinary differential equations. And we have various methods in this thing. The first method is uh, linear differential equations with constant coefficients. And the other one is linear differential equations with variable coefficients. And there are various methods like MVP and there are many more applications like LCR circuits which we use in physics and all, right, and spring mass systems. So today I'm going to discuss about uh, linear differential equation with constant coefficients. So I'm gonna say about the general form. So general form, it is t to the power y dx to the power n plus a1 into minus 1 by dx y minus 1, so on until a n y is equal to f of x. So here a1, a2, a3, so on until an. These are real constants. And f of x, any function, any random function. So like we should change this thing from general form to operator form. So better understanding. So let's take a look. Operator form. T to the power n plus a1 into t to the power n minus 1 plus a2 to the power n minus 2 plus so on till a to the power n and y equal to f of x. Here t refers to d by dx. So so for writing the solution, we usually write it in two parts, yc and yp. Yc is known as complementary function, and yp is known as partial integral. So to find YC, CF like complementary function, like there are some method, like there is a method to find this thing. So uh, m to the power n plus a1 into m to the power n minus 1 plus so on until a to the power n by f of x. Just change this thing, operate from there is a operate from here, right? So like take m instead of d, sorry, uh, take m instead of d to get this kind of an equation. So and equate it to 0. So m to the power n plus a1 into m to the power n minus 1 plus so on until a to the power n like equate this whole this thing to 0. So if n equal to 2, we get a quadratic equation. So we will have two roots, and that is m1 and m2. Now let's take a look regarding these conditions. If m1 and m2 are real and distinct, then we write yc as c1 into m, sorry, c1 into e to the power m1 x plus c2 into e to the power m2 x. Like this is a what is a kind of a general solution or something like that. And second one is like if m equal to alpha plus I beta, like if the solution is in a complex form, then we write yc equal to e power alpha x c1 cos beta x plus c2 sin beta x. So this is a solution when the roots are complex. And to find uh, yp, we have various methods that I've already told you. Uh, Operator method. Operator method and MVC is our method of undetermined coefficients. Undetermined coefficients. And the third one is MVP, method of variable parameters. So the most preferable way is MVP. We generally use MVP for this thing. So this is meant for second order differential equation. So let us consider a 2-degree differential equation. Dx square plus a into dy1 by dx, sorry, a1 into dy by dx plus a2y equal to uh, right. So here we're gonna take it as x, capital X, right? Don't confuse between this x and normal x. This is capital X. I've written to indicate this thing. So we already know yc, right? Yc equal to c1 into f1 of x plus c2 into f2 of x. Now to find yp, we write pf1 plus qf2. Now what is p and what is q? So p is given as minus integral of f2x by, so here this is f2 capital X, x by f1 f2 dash minus f2 f1 dash dx. By solving this, you'll get p, and for q, integral f1 into x, the same x, the blue x which are going to use here, right? By f1 f2 dash minus f2 f1 dash into dx. So these are p and q, and we know, right? So yp equal to p into f1 of x plus q into f2 of x. By solving this, we'll get yp and total y equal to yc plus yp. So like this, we can get the solution, like the final solution here. So yeah, so thanks for watching. In the next video, I'm going to explain a problem regarding this thing. Okay.